All right, geometry class. This is going to be our last lesson for the year for 2020, and then you're going to have a review test on chapters 7 through 9. You'll have to pick any 20 of the 25 questions. And I'm just going to kind of run through this one really quick. There's kind of a complicated section on page 437. I'm not going to go into that in detail. You can consult the book for that. All right, let's move on. So we're dealing with spheres. We kind of have to go back to chapter 8 and some of the concepts that we talked about for circles, and now we're just applying them to three-dimensional figures. So a chord of a sphere is a segment whose endpoints with endpoints on the sphere. So this is like the chord of a circle, but now we're talking about a three-dimensional object. A diameter of a sphere is a chord containing the center. So just like the diameter of a circle, now it's with a three-dimensional object. A tangent of a sphere contains exactly one point of the sphere. So just like you have tangents in circles, you've got tangents of spheres. And you can have tangent lines or you can have tangent planes because we're talking about 3 dimensions now. A secant of a sphere contains more than one point of the sphere. So again, think about your lines that go through a circle. You can have the same thing happen with a line or a plane, and it contains more than one point. A secant line intersects a sphere in 2 points, while the intersection of a sphere and a secant plane is a circle. And if that doesn't have the sphere center, you can see some illustrations of this on page 437 where you see planes intersecting the circle, one through the center, one through a slightly higher spot. So just make sure you're aware of that. All right, so here's our illustration, and there you can see a secant plane going through the sphere. This one happens to go through the center. All right, and this is how you would draw it. A great circle of a sphere is any cross-section of the sphere formed by the plane passing through the sphere's center. Okay, so the great circle is it contains the entire sphere at its largest point. Okay, so it's the actual measure of the sphere. The circumference of the sphere is defined as the circumference of a great circle. And you can see that if you rotate this plane, you could have several great circles. Okay? All right, so here we're going to talk about the surface area of a sphere, and this concept of the great circle is what helps us to be able to identify it. The two great circles illustrated by dashed curves separate the sphere into 4 sections or lunes. Okay, so you can see how you've got like a quarter in the upper right, a quarter in the lower right, right? Those are called lunes. Each one of them is a lune. And here's our theorem. The surface area of a sphere is the product of 4 and the square of the radius. So again, this is related to this concept of the great circles and the lunes. You've got 4 of them, and that's what allows us to generate the surface area of a sphere. Okay, so make sure you stop the video and repeat this a couple of times. Surface area, that's what the capital S is, equals 4 pi r squared. So it's like the area of a circle multiplied by 4. Here's our first example. The moon can be modeled as a sphere with a radius of 1,738 kilometers. Find the approximations for the circumference and the surface area. Okay, so circumference is obviously pi r squared, and then we're going to use that, I'm sorry, not pi r squared, 2 pi r, and but then we're going to use pi r squared to find the surface area. Okay, so here's our circumference, 2 pi 1738, which is 3,476 pi, or approximately 1,920 kilometers. All right. And then we can move on to the surface area. So here's the formula. We have the radius squared times 4 pi. That gives us 12,082,576 pi kilometers squared. And if we multiply out the pi 22/7, it gives us 37,958,532 kilometers squared. So that's your surface area, your total surface area. And we're doing this in kilometers because that's more often used in scientific modeling. You'll use metric measurements. Now we're moving on to the volume of spheres. The volume of a sphere is the product of 4/3 and the cube of the radius. 4/3 and the cube of the radius. So volume equals 4/3 pi r cubed. And this is the theorem on 437. And then there's a very sophisticated explanation. And that explanation is based on this Cavalieri's principle so that you can actually see. So I'll let you peruse that at your leisure. All right. Find the volume of a sphere with a diameter of 10 inches. So again, the formula again is 4/3 pi r cubed. So r here is going to be 5, right? So here's our formula, 4/3 pi 5 cubed. So we multiply that out, we get 500 pi over 3 inches cubed, which is approximately 523.6 inches cubed. So there's your volume. Again, volume always is in cubic units, cubic inches in this case. So if a ball has a circumference of 22 feet, find the ball's radius and the number of cubic feet of air it can hold. So we need to divide by pi and divide by 2 to find the radius, right? Because the circumference is 2 pi r. So we're going to divide that 2 pi onto the other side. So the radius is 11 over pi feet. 11 over pi feet, which is approximately 3.5 feet. And then we're going to use that to put into our volume. So 4/3 pi times 11 over pi cubed. So we multiply that out, we get 5,324 over 3 pi squared feet cubed, or approximately 179.8 feet cubed. That's how much cubic air a ball that is 3.5 feet. So think of a large beach ball, and it can hold that much cubic feet of air. Okay, here's your assignment. We're just going to do 2 to 16 even, number 30, which is going to be a spherical shape on top of a cylindrical shape. So again, you're gonna have to add, half of a sphere to a cylinder. So you'll be using the previous section's formula with the current section formula, but again, you're going to divide it by 2. And there's just a little review of some very basic things that goes all the way back to the beginning. Okay, so kind of short lesson, and then you got your big test, and then we're done. So God bless you. I hope you have a great summer, and maybe I'll see some of you at the graduation.